19 pandemic?
Well, now it is widespread here in California. Still, we
Okay.
are halfway in the occupancy of hospitals. I work at home
Mm-hmm.
2 or 3 days per week.
Okay,
And
okay.
currently, all non-essential workers need to stay at home.
Mm-hmm. So, so this all means all offices are work from home these days?
Yes, these days I had been at home because I had been sick, but the antibiotics
Mm-hmm.
are working now. I had a strep throat.
Throat,
Yeah,
throat infection. How is this? Is fine now?
it's fine now. I have already 2 days with antibiotics, and
Okay, okay.
I feel better. Still a little bit under the weather.
So our director would join at 11:50. So we will start nearly to that time. So sorry for keep you hold. Yeah, because he is outside, so he would join in meantime.
Good morning, sir.
Very good. Good morning, sir.
Good morning.
Sir, we have the Dr. Juan from the USA, and he would be the speaker of the first session. So let me start our welcome address. A very warm good morning to everyone present online. I am Dr. Rajkumar Arya, Associate Professor, Department of Chemical Engineering, NIT Jalandhar. I welcome you all to the week-long international online short-term course on current and future scope of surface coatings, organized by Chemical Engineering Department of Dr. B.R. Ambedkar, National Institute of Technology, Jalandhar, from 2nd of December 2020 to 6th of December 2020. Coatings are an integral part of our daily life, as most of the items that we use in the daily life are covered with a layer of coatings. The intriguing surface characteristics of coatings, even at nanoscale level, have the ability to improve a material's functionality by corrosion resistance, friction reduction, anti-fouling and conditioning it with antimicrobial property, self-cleaning, heat and radiation resistance for commercial applications. Coatings have an extensive use in our daily life as the food we consume, the clothes we wear, the medicines we intake, or the future or the furniture we use, the vehicles we drive, or the paints we use to color and beautify our houses. Each objects need a protective barriers to enhance and impart special properties to the base material, thereby boosting durability as well as beautifying the products. It is also used to augment the specific characteristics of the base material, such as functionality, strength, conductivity, magnetism, etc. The objective of conducting this short-term course is to provide insight to the students on the trending technology development, focusing on generating new areas for future scope of research and development, as well as delivering insights to latest technology and applications used in coatings. The course would act as a platform to limit and bridge gaps between the industry and the learners. This short-term course comes at a time when the students are facing difficulties in catching up with their industrial training programs due to global pandemic glaring large across the world. However, as we at NIT emphasize on one goal of imparting learning at the optimum level, this short-term course would providing some insights in the coating industry and its functionality. We have international experts from USA, Greece, and UAE, along with Indian experts from various industries, namely Asian Paints, Berger Paints, Suitom Inc. Private Limited, Tata Motors Private Limited, Jindal Polyfilms, India, who would be sharing their expertise with the participants. I thus once again take the opportunity to welcome you all to the international online short-term course on current and future scopes of surface coatings. Now, before we proceed with the short-term course, I would like to introduce the Honorable Director of Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, Professor Dr. Lalit Kumar Avasthi sir, who is kind enough to grace the inaugural sessions of the STC despite his hectic schedule. We also have the HOD of Chemical Engineering Department, Dr. Sangeeta Garg, the faculty members and the participants attending the short-term course. May I now request our convener, Madam Sangeeta Garg, Associate Professor and Head Chemical Engineering Department, to share her thoughts about the department and the short-term course. Sangeeta ma'am, please.
Thank you, Arya sir. Good morning to all of you. Honorable Director Sir, Professor L.K. Avasthi. Today's speaker, Dr. Juan M. Desantos, Senior Principal Scientist, USA, Dr. Rajkumar Arya, coordinator of the course, faculty members, and my dear participants. I welcome you all to the self-sponsored International STC on current and future scope of surface coatings. In this pandemic time, the Department of Chemical Engineering has been very active in organizing various STCs and webinars on very innovative and need of the hour topics. Today's topic is another very important area, and this is also this time we are doing the first course. This is the first course Chemical Engineering Department is doing. This is the international course and the self-sponsored also. Yeah, today's topic is very important. The Department of Chemical Engineering has come a long way after a feeble start in 1990. As on day, we have 17 faculty members, well-established labs, and latest research projects. Our scholars are working on the upcoming areas related to chemical engineering, like new and renewable energy sources, multi-phase flow, polymers, etc. We have almost 300 publications in the reputed journals. We are also working with industry through a technology transfer project in manufacturing and air purifier. With this, I wish this STC a grand success. Thank you. Thank you.
Thank you, ma'am. May I request the Honorable Director, Professor Dr. Lalit Kumar Avasthi sir, to formally inaugurate the short-term course on current and future scopes of surface coatings and motivate the participants with his words of knowledge. Avasthi sir.
Good morning and greetings from NIT Jalandhar. Our esteemed speaker, Dr. Juan Desantos, the head of department, Dr. Sangeeta Garg, Dr. Rajkumar Arya, Dr. J.K. Ratan, heads and deans. It's my pleasure to be here on inaugural of this short-term course on current and future scope of surface coating. I would introduce you to the institute. This institute came in 1987 as the Regional Engineering College Jalandhar, and later on we were deemed university, and then later we were re-christened as Institute of National Importance by Act of Parliament in 2006-7. The institute as on date is imparting quality technical education. We are basically a technical university. We have around 1135 intake in undergraduate student in 11 disciplines, and including chemical engineering. Then we have 16 MTech courses, MBA program, and usually per year we take around 100 research scholars every year. So institute is imparting quality technical education. There are many good things about the institute. We have added more than 100 faculty members. The faculty of the institute in around 11 months have published more than 500 peer-reviewed journal publications, and the institute is in top 10-11 NITs in the country. Also, we are in A band of innovation, Atal Innovation ranking. All good work of my faculty members. I congratulate all of them. Regarding this course, many small works are going on at NIT Jalandhar in coating, and definitely this is an area of importance. The physical, chemical, and mechanical properties of a material surface determine its applicability in many technical devices. Numerous applications could not be realized without the use of surface modifications, coatings, and thin film technology. Therefore, the need for efficient and effective methods of surface modification is insulation, improved optical and alter electronic properties. Coating technologies of particular interest include physical and chemical vapor deposition, thermal spraying, electrochemical deposition, sol gel synthesis, and plating. I think during this particular course, novel trends related to surface engineering and coating technology for production of functional materials, surfaces, etc., a novel fabrication method, materials, and applications, new characterization techniques as well as numerical simulation and modeling will be dealt with. And I hope that the participants, their knowledge will be enriched by the international experts who will be talking on the latest in this area. With this word, I hope everyone connected is in good health during this pandemic time, and the humanity as a whole come out of this pandemic time at an early date by having a vaccine for this COVID-19. Thank you. Jai Hind, Jai Bharat.
Thank you very much, sir. Thank you, sir,
Thank you, sir.
for
Thank you very much.
sharing your valuable inputs. The first topic of this short-term course is Fundamentals of Coating Processes by Dr. Juan M. Desantos, Senior Principal Scientist, Fundamentals and Applications, Avery Dennison, USA. Before we move on to the session with Dr. Desantos, let me give a brief introductions of our first speaker. We have amidst us Dr. Juan M. Desantos, who is a senior principal scientist at Avery Dennison, USA, where he is working for over 14 years. Dr. DeSantos is a PhD from University of Minnesota, Minneapolis. Prior to that, he received a BSc in chemical engineering from University of uh, God, Guadalajara, Mexico. After a postdoctoral stay at the University of Minnesota and Minnesota Supercomputer Institute, Juan joined as the faculty of Department of Chemical Engineering at the University of Guadalajara, Mexico. From 2011 to 2018, he led the fundamentals and applications team of the Engineering Technology Group, first as a principal scientist and from 2013 on as a technical director. Juan was chairman of the 2018 ISCST Symposium held in Long Beach, CA, USA. Since September 2020, he served as ISCST president. Dr. Juan M. DeSantos has hands-on applied industrial researchers and technical leaders. His core expertise lies in fluid dynamics, conjugate heat and mass transfer, strong chemical engineering underpinning, most recent applied to roll manufacturing processes, and previously on food engineering and post-harvest technologies. He is experienced in both experimental and computer-aided approaches and in lean design of new products, applications, and new processes. Rich experience as collaborator and leader of multidisciplinary and multinational teams as well as R&D programs and project managers. So with this brief introductions, we will start the talk from the Professor Juan. Uh, Dr. Juan, would you like to say something before I will start your presentation?
Well, yes, first of all, I am very grateful by your invitation and rest assured that any time that I could help, I will do so.
You must
Thank you very much.
guide the department and help this department to achieve excellence. We are in modification of curriculum of undergraduate, postgraduate courses. So,
Yes, sir.
how the latest technologies can be infused in the chemical engineering department so that this becomes one of the most sought departments in the country or in the world as well. So, I would seek your input from your side so that, and I will ask the head of department to be in touch and send you the curriculum which we are offering to undergraduate and take your active feedback.
It will be my pleasure,
Definitely,
sir.
sir.
So thank you very much. Now I will run the presentation of the Professor John. So we will have the presentation. So if you have the questions in between, so you can put in the drop box, I mean the chat box, and Later on, at the end of the session, we will have the question answer sessions. Hello?
Yes, we can hear you.
Uh, is this audible?
Yes, sir, now it is audible.
Okay, okay.
Yeah, you need to go to the beginning of the presentation.
Okay, okay. So- Hello?
Yeah, most probably you are having problem with the source of sound, and you are having also some feedback. Yeah, the sound is not coming, at least not in my end.
So let me do one thing. So
Are in Glendale, California, in the United States. We operate in more than 50 countries with approximately 30,000 employees. Let me see. Our $7.2 billion in 2018. Our Fortune rank is 427.
Sir, it is not audible clearly, sir.
just
I want to thank your advisors for inviting
is it audible now?
today. In what follows, I will on key technological aspects that illustrate the physics involved in many coating processes. I divide my task in 4 parts. No. First, a presentation of my company, Every Denson. Then, an introduction to continuous liquid coating processes. Afterwards, some elements of fluid mechanics and observations on rheology that are pertinent
Well, now?
to those.
Not clearly. Ask him. I'm not getting what he is speaking, sir.
No, in fact, for presentations, there should be a tab over there in Google Meet that will allow you to present and send the sound. Let me see. I am trying to Google it up. We specialize in the design and manufacture of a wide variety of labeling and functional materials. Our products are
Yes, sound is coming, but not very high. So it's good actually. Sound is wise is good.
Waters are in Glendale, California, in the United States. We operate in more than 50 countries with approximately 30,000 employees worldwide. Our sales were $7.2 billion in 2018. Our Fortune rank is 427. We have 3 major divisions. First, label and graphic materials. That produces label and packaging materials, graphic materials.
Johan, do you want to give the live presentation? Because the sound is somehow.
Yes, let me see. Just a moment. I am reading on the issue.
Okay.
That produces tickets, tags, labels, and the embellishment of retail apparel, radio frequency identification solutions, printing systems, and retail automation systems. And third, industrial healthcare materials. That produces performance tapes for industrial use, for example, for the automotive, electric, and electronic industries. Industrial adhesives, fastener solutions, and medical solutions, for example, patches. Okay, if you wish, stop the presentation on your side and let me try to do it on my end. Just a minute. Just a minute. Settings. Okay. Okay, let me see. I will try first to run the recording from here. Otherwise, I will start a live presentation. Just a minute. Can you hear?
Yes, we can.
Just let me restart and adjust the volume. Somebody needs to turn the speakers off.
Yeah.
Let me see. Uh-huh. Okay. Yeah, let me see. Let me go up to the beginning.
Joan, actually, we cannot hear the voice again. So it's
Okay.
just, yeah.
Okay, then I go live. Just a minute.
Yeah. Because this gives voice in computer, but that mic need to be placed on. So I was trying same thing. So unfortunately, volume was coming very low.
Don't worry, let me go to the different process. Sorry about that, guys. The issues of trying technologies for the first time. Just a moment.
Yeah, it happens actually.
Okay, now my screen should appear.
Yeah, it's coming. It's coming.
Okay. Let me see. Okay, let's start.
Yeah.
I will talk about my company first, just a few slides about that. Then I will introduce some ideas about what is to coat, and in particular, what is to coat with liquids. A third part of my talk will dwell upon some elements of fluid mechanics and also about some observations in rheology. I will not be, just let me see, it's going wild for some reason. My God, is presenting itself. Sorry. Let me see. What should I do here? A slideshow. And do not play narrations. Yeah. Just a minute. Again. Well, I hope that it goes better this time. Sorry, it's because it was in automatic slideshow. Let me start with a small presentation on my company. We are a global material science and manufacturing company, and we specialize in the design and manufacture of a wide variety of labeling and functional materials. Our products are used in nearly every major industry. Our corporate headquarters are in Glendale, California, in the United States. We operate in more than 50 countries with approximately 30,000 employees worldwide. Our sales were $7.2 billion in 2018, and our Fortune rank is 427. We have 3 major divisions, namely label and graphic materials, where we prepare label and packaging materials, graphic materials for banners and commercial signs, for buildings, for vehicles, and also reflective materials for road signs and personal and protective equipment. Second, we have retail branding and information solutions that produces tickets, tags, labels, and embellishments for retail apparel, radio frequency identification solutions, printing systems, and retail automation systems. And third, industrial and healthcare materials that produces performance tapes for industrial uses, for example, automotive, electric, and electronic industries. We produce also their industrial adhesives, fastener solutions, and medical solutions, for example, medical patches. Among other things, we made thousands of variations of products that have at least 4 layers, like here. And among them, we have rigid films that are used for a wide variety of rigid plastic and glass bottles like beer, juices, and teas. Squeezable films that are used to decorate squeezable containers like those of shampoo bottles and tubes in the home and personal care segment. Coated papers encompass a broad array of segments and applications from wine, spirits, food, pharmaceutical, and many others. Finally, thermal papers are used in countless applications to convey information and enable supply chain efficiency, from warehouse to shipping and tracking, and also to weight scale applications to specimen and script labels in the clinic and pharmacy environments. Now, how we do this? As I mentioned, many of our materials have at least 4 layers. Let me start from the bottom. The release liner is usually a film or a sacrificial a paper stock. And it's sacrificial because when we peel it for application, we discard it. So there is some incentive to find alternatives to this. Then we have a release agent that is coated over the release liner. And usually these are silicones or it may be also casted polyolefins that have very low surface energy. Then for us, one of our mainstays are adhesives, and we offer them in many kinds. And well, this is basically our sticky stuff. And we coat the adhesive usually over the release liner, and over it we usually laminate a face stud, which may be fine paper or a printable film. Below, I show one possible way of doing this, where we have the liner, we unwind it, we siliconize it, we cure the silicone, then we coat the adhesive on the silicone side, we dry the adhesive in one of the configurations, and then we laminate the face, and we wound up the finished product. That's one possible way of doing it. Let's consider some basic ideas and terms that are related to liquid coating processes. I focus my talk on processes for the so-called continuous liquid coatings, which just means that all the relevant surfaces on the substrate, at least on one side of the face, are covered with the coating which is supplied as a liquid. Specifically, I will talk about modern roll-to-roll processes in which the material substrated or web to be coated comes in rolls, and these rolls are large and often have several tens of kilometers of winded paper stock or polymeric film. I list here other coating processes, whether using liquids or not, that are important, but they are not the focus of my presentation today. Now, what is to coat? To coat, the late Regents Professor Escriben, to coat is to replace gas at a solid surface by layer of liquid. Generally, the layer is required to be thin, 10 to 100 micrometers, and in some instances 5 micrometers or maybe less. And it has to be continuous. The outstanding exception is to print, because to print is to coat discontinuously. Well, this sounds simple, but there are challenges, because we want to coat defect-free, and this means a very uniform coating as is measured by a specified thickness or coat weight, and this implies that coating flows are mostly two-dimensional flows. Also, quality coatings require to be free from bubbles or blisters for performance and or aesthetic reasons, and the coating must be free of dry or dewetted spotted lines that are not intended. We want to do it as fast as possible, and a further complication is that nowadays we have moved to thinner coatings as we are enabled by high-performance materials and better processes, and as the economy dictates. But these thinner coatings are more challenging when you want to coat them faster. Now, why do we coat? Well, the answer is simple. Coating performs functions. Top coatings, always the outmost layer, which may be protective, may allow printing quality, may be applied for aesthetic reasons, may confer special wettability properties, for example, anti-smudge, smash, and other functions or combinations of functions to interact with the world. Then we have the so-called tie or primer coatings, which are intermediate layers applied to enhance interlayer adhesion or anchorage. Other kind of coatings that I want to mention here, among the many, are the release coatings, which I mentioned before, and they have very low surface energy and are commonly used to release adhesives from the liners. I want to mention, because of my company, adhesive layers, which are sticky layers that adhere to target surfaces. There is a great variety of formulations and strengths. They range from strong and permanent to weak and repositionable adhesives. And many other functions performed, for example, by the layers of flexible electronics, battery separators, structure layers, barrier coatings, etc., etc. Many kinds available, optical properties, etc. It's a plethora of possible functions. Now, regarding the liquid coatings, according to their composition, the liquid coatings may be polymer solutions, whether water or solvent-based. They can be suspensions, either colloidal or non-colloidal character, and they can be molten polymers. If the liquid are solvent-based, we need to exert special care for to have a safe process. When I say colloidal, what I mean is that the particles in suspensions can undergo Brownian motion, so their size is roughly up to 1 micron or thereabouts. In the case of polymer melts, higher temperatures are applied, and the processes are more complex to control the heat transfer. And this is important because if we don't control heat transfer well, it could cause unevenness of material properties and even solidify the melt prematurely. Now, composition affects the coat weight and coating thickness. The final dry coat weight depends on the percentage of solids at room temperature in the liquid composition. For example, a molten polymer has 100% solids. Whether dry or wet, the coat thickness, on the other hand, depends on the density of the mixture. Rule of thumb, for polymers and other substances with a density close to that of water, the coat weight is about 1 gram per square meter per each micrometer of coat thickness. Roll-to-roll manufacture consists of various unit operations. The name roll-to-roll manufacture originates because we start with a substrate web that is wound in a roll, then we coat it with a suitable liquid, and after the liquid solidifies with this, over the substrate, we wound it again in a roll of finished product. The film material may undergo a series of treatments along the wet path. Before coating, for example, we can apply plasma or corona treatments to improve adhesion of the coating to the web. At various stages, for example, here and here, we can have charge neutralization in case our process needs it. Now, solidification of the liquid coated has to be achieved, and it may require cooling, for example, for hot melts, drying in the case of solutions and suspensions, curing, as is the case in silicons, for example. And sometimes, even after it is dry or solidified, may require some annealing so that the properties of the finished product are attained. Now, the coating liquid also requires careful preparation to deliver a well-mixed, bubble-free liquid at a consistent temperature. Ultimately, the target is to coat uniformly at a desired dry coat film thickness specified in micrometers, or a dry coat weight specified usually in grams per square meter. Each operation has to be carefully designed and tuned to deliver a defect-free product. Now let's focus on the coating operation. Liquid coating methods can be classified broadly into groups: cell meter, shown here, and pre-meter. Let's go back to cell meter. In cell meter coating methods, the coated wet film thickness, here, 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 is set by a complex interaction of process variables and coating liquid properties. For example, in the many roll coating methods, like this one. Also, in the case of knives, blades, like this one, membrane, and for example, this coating, this one. Usually, a liquid feed is provided to maintain a certain level in a pool or puddle of liquid from which it is picked up. Here I show an instance of a roll coating that is called forward coating because the rolls move in opposite direction. The place where the rolls are nearer to each other is called the nib, and there the liquid is split into films. One is a reject that returns to the pan, and the other is applied up on the web. Here below, I show a case of blade in which the cutway is the product of the equilibrium of viscous, capillary, and elastic forces. Usually, in this kind of applications, there is an excess of coating applied first to the web, and the blade is used to meter, to doctor the ultimate cut weight that is delivered, and there is a stream that is rejected. Below, I show deep coating, in which basically there is a pool of liquid, and the wave dips into it and picks up a given amount of liquid, which is basically doctored by this sharp meniscus here, in an interplay of viscous, capillary, and gravitational forces. So it's a complex interplay that needs to happen to deliver a given cut weight. Now, perimeter coating methods are more reliable because functions here are separated. The average wet film thickness is determined by the measure, this is metered flow of liquid that comes from a suitable pump, a positive displacing pump. The uniform distribution across the web is performed by a sturdy chunk of metal that is called a die. This is the magic of the perimeter methods, such as slot, slide, and contact. So again, the total flow rate is given by a pump, but the distribution across the web happens in the die. So greater precision, and both in the pump and in the machining and positioning of the dies is required, and this means greater cost, so greater capital cost. Let's look with a little more detail to coating methods to see what's going on. First, let's consider a two-roll reverse coater, in this case fed by a pond of liquid. I'll use words upstream and downstream which relate to the movement of the web. So downstream will be the side where the web approaches the liquid, and downstream will be the side where the web departs. I mentioned this because if you look at from the point of view of the liquid can have different paths. So for clarity, let's refer to the movement of the web. So we can distinguish a region where most of the action happens, the strong part happens, the metering of the final coating will happen. And this is called the coating bead. Here, the flow is almost parallel, but there are strong gradients in the direction perpendicular to the flow path. Now, there is also action here in the pond, but the velocities there are relatively weak as compared to the strong gradients that happen in the coating bead. In the place where the wet plunges into the pond and is first wet by the liquid, we find what we call a dynamic contact line. It's a place where we force the wetting upon the web. There is also a free surface in the downstream part, that the parts from the coating bead, eventually the gradients relax far enough from the coating bead, basically all gradients disappear, and the velocity profile is basically a fluid flow, is a fluid flow, and it insists in going back and moves at the velocity of the web. Now, a second case. Here we see an schematic, not to scale, of a slot dicoter. Again, the designation upstream here and downstream here are with respect to the wave trajectory. Upstream is on the wave approaching side, whereas downstream is on the wave departing side. Inside, we can distinguish two types of flow. One type inside the die, which function is to provide uniform lateral distribution in the direction perpendicular to the plane shown here. These flows are called interior flows, and they start from the place where we feed the liquid from the pumps and finish in a narrow slot that delivers the liquid to a required width, which must be slightly less than the web width. Again, when I say width, I refer to the direction perpendicular to the plane shown here. Then there are the exterior flows. So basically, you can distinguish here the coating bead, that is the region between the lips of the die and the moving wave. The moving wave here I show supported by what is called a backup roller, BUR. Now, in the coating bead, we distinguish also the point where the wet meets the liquid for first time and where forced wetting happens, and is called the dynamic contact line. Now, notice that here the meniscus is basically cylindrical. I say cylindrical even if you see an arced circle, because you have to remember that there is a depth to this drawing. And meets and hopefully anchors to the upstream corner of the lip. There is also a downstream meniscus that starts from a static contact line, shown here pinned to the downstream corner of the die. And again, eventually, gradients relax, and we attain the velocity of the wave in translational movement. Now, precision matters because you have films, you have films that are 10 to 100 microns and similar dimensions in the bead and in the slot. Now, to give an idea of what this means, here I am showing, this schematic represents a human hair, which is about 90 microns. We are looking for precisions close to that of 1 micron, which I show here. And the reason we need such high precisions is because small variations in die geometry and position can affect strongly the local thickness and cut weight of the coated or casted film. That's the reason why these methods are better, but they are more expensive. Now, let me tell you a story. Coating technology has evolved from an art to a science, and it has been driven mainly by the needs of the photographic industry, mostly in the 20th century. This is well attested by the patent record, where we find the milestones of modern coating technology. By the end of the 19th century, photographic paper was coated by deep coating, where wet was submerged into a pool of liquid, and where the coat weight depended on the material properties and process speed. Ovens were quite inefficient because there had very little convection. And thus, here festoon dryers were invented, and basically these accumulators served to increase the residence time of the coated films in the oven. By early 20th century, wire-wound rods were invented, the famous Meyer rods, which are still used in several manufacturing processes, mainly of specialty papers. By 1945, there was the invention that preluded dies, when Eastman Kodak patented a knife spreader fed by a hopper. From this, there is a quick succession of patents toward dies here. In 1954, in a similar patent, Begin invented coating methods with a vacuum box, either for roll or die coating. By controlling the upstream pressure, Begin's invention expanded the set of operating conditions under which coating was successful, the so-called coatability window. Now, non-contact curtain coating evolved for coarse method for good processing and even food stuff coverings. But by 1972, Eastman Kodak filed the patent for a fine, precise, well-controlled curtain coating that can reach very significant speeds. Now, the drive towards thin, defect-free coatings have caused the evolution of die coating. Here I show the so-called tension wave over a slot die, where a wave is kept out over the die lips, which are wet by the coating liquid in a feat of elastohydrodynamic lubrication. Industrial dry continues as coating becomes thinner and speeds rise, and with refresh interests and challenges driven by roll-to-roll manufacture of flexible electronic materials. There is another side to the story, and it's academia. Academia has been key in developing the science of coating, starting with the work of the early Russian pioneers that investigated dead coating. Among them Lev Landau, a physicist Nobel Prize winner. Dead coating was then further studied by Talmach at Yale. Probably the most impactful research group in coating flow was that led by the late Skip Scriven at the University of Minnesota, where it still continues vigorously by the work of Satish Kumar. And also Marcio Carvalho, who works in Brazil, but still is a continuous visiting professor at Minnesota. Other alumni of the group, now they have their own works. More I want to talk about of a joint researcher, gentleman, Nam in Korea, and even the great styled middleman in his early career pays some attention to roll coating. Other important groups are those in Taiwan and the several groups in the United Kingdom, particularly the University of Bradford and the University of Leeds. Similar diagram can be made for drying, but here I state on the coating realm. Now, what you should remember, I hope, of what you listen now, is that to coat is to replace gas at a solid surface by a layer of liquid. That roll-to-roll manufacture consists of unit operations from web and winding to finished product rewinding. In between, it involves coating, coating solidification, lamination for sticky coatings, and other treatments at various stages. Liquid coating methods can be self or pre-meter. Self-meter are those methods where the coat weight ensues from a complex interaction of liquid properties and operating conditions. In pre-meter methods, the average coat weight is set by a pump, and the cross-web liquid distribution is performed by a precise sturdy chunk of metal called a die. Since the later part of the 19th century, roll-to-roll coating processes have evolved from art to science. This evolution has been driven by industrial needs, particularly those of the photographic industry in the 20th century, Not anymore, but well, it was like that, and brought about by industrial researchers. The fundamental understanding has been enabled by efforts of scholars at various academic institutions. Let's review now some elements of fluid mechanics and some rudiments that are relevant to liquid coating. I have to be clear that my intention is not to teach you fluid mechanics here, but just to allow you to attain a qualitative understanding of the fundamentals behind coating flows. The main points here are that by design, because of the requisite cross-wave uniformity, exterior coating flows are ideally two-dimensional and steady. Now, there is an issue. Most defects are three-dimensional and even transient, breaking uniformity in some sense. Then coating flows involve free surfaces. This is gas-liquid interfaces. And there is at least one front where the liquid dynamically replaces the gas, generally air, that lies over a solid substrate. This is called the dynamic contact line. If the coating occurs at high enough speed, air can be entrained into the coating as small bubbles, which may or not dissolve into the liquid. Now, coating are slender. So, as the liquid flows to coat a substrate, there are slender sections where the velocity gradients happen in the direction perpendicular to the moving wave. This is the reason why simplified one-dimensional models often suffice for analysis. If you decide to study coating flows, this simplified analysis may be your next step. Now, the flow of fluids is governed by both mass and momentum balances. The mass balance simply states that the rate of accumulation of mass per unit volume is equal to the net convected influx per unit volume. Now, convected means transported by the bulk movement of the fluid. Here we consider that there is no migration of any of the components of the fluid. Otherwise, we will need to add additional equations for the mass balance of species. The momentum balance states that the rate of accumulation of momentum per unit volume is equal to the net convected influx of momentum per unit volume plus the net rate of momentum influx by molecular transport, which is statistical in nature, plus the external forces per unit volume exerted on the fluid, commonly gravity. And of course, there are cases where the consideration of energy balances is unavoidable, as is the case of molten materials. But here, let's keep it simple. Now, for incompressible constant density liquid flowing at a steady state and in isothermal conditions, the balance simplifies. There is neither increase of mass per unit volume nor increase of momentum per unit volume. Also, density is constant and can be taken out of the operators. Now, again, if there is significant heat transfer, like in molten materials, the isothermal assumption may not hold, and an energy balance needs to be considered. Now, we had mentioned stress. Stress traction over a given surface is a force vector per unit area transmitted by contact. And contact ultimately arises from molecular interactions. Stress traction can be decomposed in normal and tangential components, which are called shear. The normal part can be tension, if it is pulling on the surface, or compression, if it is pressing on the surface. Again, the tangential part is known as shear stress. Stress has the same units as pressure. In fact, pressure is one of the components of stress in a continuous media. An ideal fluid, by definition, cannot stand shear stresses without flowing. only normal stresses appear in fluid statics. But some real liquids can. For example, yield stress liquids that only flow after a critical shear stress is reached. Below that threshold, they behave like solids. Now, the state of stress in a liquid, in a fluid in general, is given by tractions on each of the three independent spatial directions. This means that the state of stress is a tensor. Stress tractions are forces per unit area on any given surfaces, and as we said before, can be decomposed in normal and shear stresses. The normal stresses can originate on pressure, which is isotropic. This means that they are the same from any direction, or can be anisotropic, which are just caused by viscous transfer, which are dissipative and statistical in origin. In some liquids, elastic molecular interactions are significant, due, for example, to the uncoiling of large molecules, as this happens, for example, in polymers. As we mentioned before, the state of stress is a tensor, as it has magnitude and two associated directions. One corresponds to the possible independent orientations of surfaces, and the other with the independent directions of application of stress tractions. Each direction can be decomposed in components in the particular system. It is common to choose the coordinate planes as reference planes, and they are identified by their normals. For example, the x-theta plane here is identified by this normal that goes along the x direction. Here I show the total stress that can be decomposed into parts. One is isotropic and is called pressure. I show here the matrices associated to the tensors for simplicity. Pressure acts equally on any plane regardless of orientation, and its matrix is just a diagonal one, and basically all the terms are the same, and they correspond to a scalar pressure. Now, the other part is viscous stress, and each of the rows of the viscous stress corresponds to tractions over each of the coordinate planes. But of all these 9 components, only 6 of them are independent because of symmetry. Over here, I reflect also that fact. Now, you can get the handout from Raj Kumar, and when you have time at home, you can analyze this. Here I describe the nature of each of the components of the viscous stress, so that you can go through this at your leisure. But enough of this. Let's simplify a bit. As successful coatings are two-dimensional. Do you remember? So let's abandon the three-dimensional work and go to 2 dimensions. If the flow is two-dimensional, the action occurs only in a plane, say the plane is y, shown here. The direction θ is pointed out of the drawing. The stress tensor has only 4 components due to symmetry. The viscous stress has only 3 independent elements, 2 normal, tau xs, tau yy, and 1 shear component, tau xy, which is equal to tau yx. So much simpler, and again, here I describe the nature of each of the components. Now, the viscous stress tensor, the components of the viscous stress tensor, depend on the nature of the liquid. One simple kind of fluid is called Newtonian, after the constitutive law proposed by Newton. It simply states that the shear stress is proportional to the rate of shear straining. The rate of strain is the rate of change of fluid speed in a given direction with respect to another coordinate direction. Here, the velocity in the x direction, and how it changes with the direction y. Now, the proportionality constant is called viscosity. In fact, shear viscosity. The schematic here shows how the momentum from a moving wall, this is a momentum source, is transferred diffusively down through the from the faster to the slower layers of the liquid. In turn, the liquid exerts shear upon the lower wall, which acts as a momentum sink. Some liquids are Newtonian, but many are not. And in general, the stress tensor can depend in complex ways on both the rate of strain, that is the speed of deformation, and on the strain tensor, that is the deformation state. Now, for the normal stress, Newton constituted equations, at least the way we have extended it, defines also that the normal stress is proportional to the rate of tensile straining. The proportionality constant is the normal viscosity, but it is just equal to twice the shear viscosity. Sorry about that. When the flow speeds in a construction, tensile viscous stresses arises as the change of liquid velocity in the flow is positive. When the flow slows down in an expansion, compressive stresses arises, and the change of fluid velocity in the flow direction is negative. Now, why does a fluid flow? Well, there are several reasons. One is mechanical potential gradients. They cause flow. These arise when pressure is not balanced by body forces or accelerations. That is gravity, linear acceleration, centripetal acceleration, etc. These include cases when something changes the fluid density, thus changing the position potential in the force field or accelerated frames. Now, relative movement of an object in contact, whether solid or fluid, can also cause flow. This is because of continuity of velocity and shear stress across interfaces. At a wall, the fluid typically assumes the velocity of the wall. This is known as the no-slip and no-penetration conditions. For a stationary wall, this means that the velocity is null. Surface tension gradients at interfaces, which arise from thermal or compositional gradients, also cause flow. In coatings, these might lead to coating defects as they produce local thinning or thickening of the coating after deposition. Another cause of flow is the movement of fluid components, either solid or in liquid form, which also may cause flow. For example, diffusion that changes local density, also, for example, bulk particle migration, electrophoretic movement of ion components, etc. Let's consider the change of mechanical potential of a fluid, and it is defined as the sum of pressure change and the change in positional potential, gravitational in this case. Now, here at the left, I show an astatic case, which means no flow. The liquids are at rest in a container. At the top, let's say that the depth coordinate is 0. The pressure here is atmospheric. At the bottom, here, the pressure is larger and equal to the pressure at the top plus the density of the liquid times the depth of the container. So pressure increases as you go down into the liquid, but the gravitational potential diminishes, such that there is no net change in mechanical potential. Thus, there is no flow. At the right, there is a schematic of a dynamic case, the flow of liquid in an horizontal slot of gap height h and length L. Between corresponding points from inlet to outlet, there is no change in gravitational potential. So flow must be caused by pressure. If there is no pressure change, there will be no flow. Liquids flow in the direction of the pressure gradient from the high to the low pressure. This problem has simple analytical solutions for Newtonian fluids, which basically you get a parabolic profile, as you already know. Below, I show simple expressions for the flow per unit width in the direction to the drawing, and the shear rate at the top wall. Notice that the flow rate is proportional to the pressure gradient here, and is proportional to the cube of the gap height, and inversely proportional, of course, to the viscosity. Now, let's pay attention to this proportionality to the cube of the gap. It means that, excuse me? Excuse me? Excuse me?
Yeah, go ahead. Actually, that mic was off. Unfortunately, you can continue.
Okay, so this actually means that given the same pressure gradient, 8 times more flow will occur if the gap is double. Okay, now let's consider a case in which the flow is caused by movement of a wall. This is called a Couette flow. I forgot to mention something. This kind of flow is called Poiseuille flow. And now a Couette flow. At the left, I show a special case of flow in a slot where only the bottom wall is moving at the speed u. If no pressure difference is imposed from left to right, the only cause of flow is the movement of the lower wall. This is a case of a so-called rheometric flow, because the flow profile is independent of the rheology of the liquid. Well, at least for well-behaved homogeneous liquids. The velocity profile is linear, and the flow is simply half of the gap height times the velocity of the lower wall. The shear rate is constant, and its magnitude is just the wall speed over the gap height. Viscosity doesn't affect the velocity profile, but it of course affects the traction needed to keep the wall moving, as shear stress is viscosity times the shear rate. So a fluid twice as viscous will have exactly the same profile, but the traction needed to move the wall is twice as big. At the right, I depict the case where, in addition to the movement of the wall, in addition to the movement of the wall, I am imposing a pressure difference. This is a Couette plus Poiseuille flow. Now, for these simple configurations and geometries, the governing equations become linear. So superposition of the solutions applies, as you may see later on when you review the handouts. And you compare the expressions for flow and shear rate, and you will see that they are just some of the corresponding expressions for Couette and Poiseuille flow. Now, the important thing here is that what I am showing you here is basically what is happening in the slot die width. So this is an elemental flow that we see often in coating flows, at least as an approximation. Let's consider another case of wet flow, where both the walls move in opposite directions, here and here. Sorry, I am pressing the wrong buttons. This kind of flow approximates that happens in the nib of reverse roll coating, where the flow is almost parallel flow, more so for large rollers. Now, again, this is a rheometric flow. The velocity profile is independent of the rheology, again, for well-behaved liquids. And here I show also simple expressions for the total flow and the shear, where the speeds of the walls assume that they are positive when they go in the assumed direction reported here. The related, well, all these wet flows that I am showing you are not commonly used for measurements because they cannot be kept in motion indefinitely, because eventually you need to stop sliding one wall. Of more important use for rheology will be the related rotational co-ed flows, as happened, for example, in plate and plate rheometers or cone and plate. Now, let's talk a little bit about what happened at interfaces. And it's the phenomenon of surface tension. At liquid interfaces, a force tangent to the interface arises. But by bending the interface, the surface tension forces can balance pressure, viscous stresses, and even stresses due to electric charges. In the absence of other stresses, pressure is always greater inside a drop or bubble. In other words, pressure is greater in the concave side of an interface. Here I show a very simplified Young-Laplace equation where viscous stresses, surface tension gradients, and electrical fields are neglected. The pressure inside a concave liquid surface is greater than the pressure outside by a term equal to twice the Gaussian curvature times a property called surface tension, which has units of force per unit length. Don't worry about this Gaussian curvature. For today, it is enough to consider one simple case, that of cylindrical interfaces, which are good approximations of the many sides that arise in coating flows. For this cylindrical many side, the inverse of the cylinder radius is twice the Gaussian curvature. That's simple. So across a cylindrical interface, the pressure inside the concave side is equal to the pressure out plus the surface tension over the radius of the cylinder. Other simple cases are those of a plane interface, where both pressures at both sides of the interface are equal, and the case of a spherical interface, where the capillary pressure jump is just twice the surface tension over the radius of the sphere. Now let's talk about wetting. Consider first a drop over a flat homogeneous solid substrate. When the drop shape reaches equilibrium, the air-liquid-solid contact line is static. This contact line is the boundary of the wetted material, is the boundary of the wetted solid, but here in 2 dimensions corresponds to just these 2 points. But it goes all around the solid, all around the droplet. Now, the contact angle is the angle that goes from the substrate inside the liquid and goes to the tangent of how the liquid air interface at the contact point. If the contact angle is less than 90 degrees, we say that the liquid wets well the solid. If the contact angle is larger than 90 degrees, we say that there is poor wetting of the liquid to the solid. Now, if the drop is not in equilibrium, it will retract the wet. And if the droplet wets well the solid, it will spread, which means to wet a larger area. Spreading happens by forming a very thin precursor film, and here I show what happens in the nanoscale. And this precursor film is first formed by evaporation and condensation. After this precursor film is formed, then the bulk of the liquid advances, and what you see microscopically is this advancing front, but in fact you are inflating, let's say, this very, very thin nanoscale precursor film. But this happens very slowly, and it's not what you usually see in the case of coating, when you really force wetting. Now, consider a drop that slides over a flat homogeneous solid substrate. Under movement, the contact angles and contact lines are called dynamic. At these dynamic contact lines, the contact angles are different than those in the static case. At the back of the drop here, the receding apparent contact angle is smaller than the static contact angle. At the front of the drop, the apparent dynamic contact angle is larger than the static case. Now let's see what is going on there in those fronts of wetting and dewetting. Now, in the wetting front that occurs in the back of the droplet, if the speed is large enough, the liquid will leave trails that break into droplets, which you may have witnessed in the shower walls as water droplets slide down. In the wetting front here, if the speed is large enough, air invades the liquid, and these air tongues then break into bubbles into the liquid. Smaller bubbles will dissolve readily, but larger bubbles will persist. In summary, when forced, a liquid can wet a substrate, even if the static contact angle is unfavorable. But as the dynamic wetting occurs at faster rates, air will be entrained. Now, consider now the equivalent case in which the sliding droplet remains in position while the inclined substrate slides outwards. Just a case of relative motion. As before, where the force dewetting occurs, the apparent contact angle is less than the static contact angle, whereas in the forced wetting, in the forced wetting region, the apparent dynamic contact angle is greater than the static contact angle. Now, imagine that somehow the substrate speed increases while the drop remains in place, for example, by increasing the inclination of the slide. Then the dynamic contact angle changes. It decreases further at the forces the wetting front and increases further at the force wetting front. Now, there are several empirical models for the behavior of apparent dynamic contact angle. As an example, I show here that model of Brake et al. That is more or less accurate. Now, you have noticed that I keep saying apparent dynamic contact angles. It is because the dynamic contact angles are macroscopic time average features, which do not represent the phenomena in the meso and microscopic scale. I want to close the section on capillary action by mentioning a surface tension mechanism that is helpful in coatings, as it allows leveling of films that for some reason were perturbed. For thin films, the mechanism may be too slow and the coating may dry or otherwise solidify well before the leveling occurs. Here I show periodic perturbations of the field thickness. Notice that the pressure just below the concave crest must be greater than the pressure just below the convex valleys because of capillary action. Thus, pumping liquid happens from the high pressure side to the lower pressure side, and this will tend to level. Now, we can model as an approximation all of this by simple one-dimensional models that I am showing here, just to give you an idea of how this is approximate. But of what I show here is that after solving all of this, we find something like this. The rate of leveling is directly proportional to the thickness at the third power, while it is inversely proportional to the wavelength of the perturbations to the fourth power. This means that with respect to a reference coating thickness, a coating half of that thickness will level at 8 times its lower rate. Also, with respect to a reference disturbance wavelength, another disturbance of double the wavelength will level at 16 times its lower rate. So, short waves level much faster than long waves. Okay, now you have many of the key elements that are at play during coating. Here I show a typical flow in a slot die. The internal flow is parabolic, is a Poisson flow, and you can see that the profile is parabolic. The flow rate per unit width, as fed by the pump, is denoted here by Q. Now, the moving web goes outwards, and so you know now that what we call a stream is in the lower part, and the stream here is in the upper part. Here, the upstream meniscus is pinned in the lower corner of the die, and it meets the moving web at a place of force wetting that is called the dynamic contact line. Now, when I say pin here, it's because maybe microscopically you perceive here as a sharp corner, but there is not really such things as sharp corners. In fact, a corner should have some radius of curvature, and often they are not even smooth, they may be rugged. And this radius of curvature of the roughness that may happen there allows for the meniscus to move slightly around this corner and still satisfy the requisite static contact angle. Now, the coating bead between the lips and the moving web, we distinguish two parts, one upstream and one downstream. In both regions, the flow is a combination of co-wet and Poisson flow. In the lower region, the higher pressure at the, let me show you the pressure first. It will be better this way. Now, here you see in the horizontal axis pressure versus position along the web. Now, on the back, just inside in the liquid, the pressure is almost that of vacuum. It's slightly less because there is a capillary correction. And it goes up to the pressure where the feed slot delivers the liquid. And then it goes down, and the pressure here at the downstream segment is almost atmospheric, well, a little bit less than atmospheric because of the curvature there of the downstream meniscus. Now, in the upstream part, the larger pressure just in front of the slot will pump liquid backwards, so it will go to the upstream part, and then the wave movement will force it up again. Now, the co-ed flow here opposes the Poiseuille flow, and the net flow must be zero, because otherwise there will be depletion of mass here, or maybe dripping, which may happen, but is not desired. So you keep conditions such that the flow, the net flow here is zero. Now, over here, you have a net positive flow, and this flow must be the same that you are delivering from the slot feed by continuity. Now, the downstream meniscus detaches from the upper corner of the die, and again, eventually it will relax all gradients, and the liquid will move basically in just a translational fashion with fluid flow equal to, with a velocity equal to that of the wave. Well, that's what is basically happened, and as you see, the main action in a slot is well described by the very simple flows that I am showing you. Well, at least to a very fierce approximation. Now, I have a challenge here for you. But in fact, to complete that challenge, my recommendation is that once you get the handouts, review them and see if you can answer by yourself.
Excuse me.
Yes?
Is this die we use only vertical, or we can use it in any direction, maybe horizontal, inclined?
You can use it in any direction, because if you remember, the dimensions that we are talking here are microns. You see, so gravity basically had no effect on the cutting bit.
Correct.
Yeah.
Okay.
So no position. And outside of this, also you need to remember that the film is very thin, so you may consider basically fluid flow, because unless your cutting film is very thick, then you may see some action of gravity. Yeah. But
Okay.
also you may control that with the rheology of the fluid. But I will mention more of that. If you have a thick coating and you don't want to see it running down, usually what you have is a shear thinning fluid where the viscosity is larger at low shear rates, so that, again, it will defeat gravity because of its greater viscosity. But it's a very, very, very good question. So gravity doesn't have a bearing, at least on the physics of the cutting bit. Now, the challenge is like this. Let me go back. Where is the dynamic contact line, and label it? Well, you already know that the dynamic contact line is the place where the wave first meets the liquid. It's a place where force wetting occurs. Now, the second part is there because I want you to have an idea of the magnitude of the shear rates that is happening here in the cutting bit. And it is telling you a case that is not far from reality. I say not far, but in fact, I can tell you that we cut much faster than this. But if you imagine that the gap is 100 micrometers, that is 0.1 millimeters, If you assume that the wave speed is 5 meters per second, this is 300 meters per minute, and if for some reason the pressure here is just atmospheric, so that there is no Passaic flow, so the flow is purely coed with these assumptions, it is asking you, well, under these assumptions, what is the shear rate? And you will find, if you make the calculations, that in those conditions, the shear rate is 50,000 reciprocal seconds. So forget about characterizing your coating liquid with a low shear equipment, for example, brute field. You will be too far of the conditions at which coating is really happening. Still, you see these kinds of things, people trying to make sense and measuring low shear viscosities, but I am telling you, it makes no sense. Now, excuse me. If the volumetric flow per unit width is Q, how it is related to the well-developed field thickness stream here? And, well, it's very simple. Basically, since the liquid moves at the same speed as the wave, then the thickness will be the flow rate per unit width over the speed of the wave. So just elementary mass balances apply here. Now, if the interfacial stresses are negligible, if you can neglect them, what are the pressures just inside the coating bead? Here and here. Well, you know already that they relate to the pressure outside, but by a simple John Laplace equation that I am showing you here. So the pressure here in the downstream part, just close to the meniscus, is almost atmospheric and is slightly reduced by capillary action. Excuse me, I am pointing to the wrong one. This is the pressure here. The pressure here is very similar, but you may notice that downstream you may apply vacuum. The reason you want to apply vacuum is because you want to pull this meniscus to this position. You may say, well, why don't you allow it to go, let's say, here? Well, the answer is very simple. If you allow it to go here, then you are just on the edge of making the flow unstable. Any perturbation will allow for the flow configuration to break up, and then dry lines will appear in the coating. So we want to keep it here, and that's the reason why in the invention of bagging, applying vacuum here was a great advance, because it allowed to coat at much greater speeds. Now, I have been telling you again and again that if you go too fast, you will entrain air here. And when you entrain a lot of air, your coatings become very unsightly. And the worse it depends on the function of the coating. For some coatings, it may not matter. But in many coatings, it matters to be bubble-free. And there is a speed at which you want to control the air entrainment here. I just want to let you know that there are ways to control that. I mentioned already a simple way, that is vacuum, but even if vacuum is not enough, you can still apply what is called electrostatic assist. Because, as I mentioned, the John Laplace equation that I showed you is very simplified. In fact, you can pin the upstream meniscus in place by applying a high voltage electrostatic field. But well, that's beyond of the scope of this talk. Now, the challenge continues. And it says that, because of continuity, because of mass balances, the net flow in the upstream section of the cutting bead has to be 0. So this requires that the pressure here upstream needs to be smaller than the pressure just under the slot, so that the Poiseuille contribution pumps liquid down and then is picked up by the wave. And here I see the velocity profile. So the net flow rate is 0 with a net Poiseuille contribution down and an equal magnitude contribution of coed up. Now, it is asking us in the second question to draw the sketch of the velocity profile in the feed slot, this part. And you know already that it must be parabolic. And in feed, it is very nearly parabolic, and it only departs from parabolic once that you are very close to the exit of the die. So it is a quite good approximation. Now, the last part is a little bit more complicated to go orally through it, but it says that under the downstream meniscus, the flow rate needs to be equal to the film thickness times the speed of the flow. And it has a series of assumptions, and I will show the answer here. Yeah, and this basically, yes.
But suppose we are getting parabolic profile through the die.
Yes.
So if we have flat profile, so did it give some better finishing of the coating or as compared to parabolic one? Because we can control the pressure gradient, and that can make it maybe flat profile. I hope so, right?
Well, what happened is that you cannot control independently because, as you see, excuse me, let me go back. For stability of the upstream part, you need a larger pressure here so that liquid is pumped in this direction and returns. Otherwise, you will make the bead unstable. In fact, it is not that important whether it is flat or parabolic. I don't mention it here, but what is more important is that you don't have recirculations, because really small vortices recirculations are like small centrifuges.
Yeah, your wave is means continuous in the motion, right?
Excuse me? Could you repeat the question? I think that I lost you.
This wave is continuously in the motion, right? So I hope this parabolic profile will not create the problem, right?
No, it doesn't create a problem at all. It doesn't really matter.
Yeah.
You see, I mean, it just happens. We don't even try to control it. What we try to control is the design of the geometry to avoid vortices, but that's a more complex issue. And the reason we want to control vortices is because vortices, small gyros there, act like centrifuges. And centrifuges there may accumulate air, yeah, because, and also they may induce migration of particles, etc. So, as long as you don't have swirling vortices inside the bead, you are in good shape. So,
thank you.
You are very welcome. Now, some comments on the rheology of coating liquids. Now, by design, coating liquids should have a relatively uncomplicated behavior, and they are often shear thinning. I will dwell upon this more later on, but this means that the viscosity decreases with shear rate, which is good for the coating processes. Now, the fact that they have relatively large viscosity at low shear rates is good to avoid running down as the wet climbs to the dryers. I mentioned that, and in thin films it's not an issue, but in thicker films you really want a greater viscosity to avoid rundown. Now, two apparatuses are commonly used to characterize the liquids. Rotational rheometers for ranges up to 5 or 10,000 reciprocal seconds, and capillarity rheometers where the liquid is forced by a piston down and it flows to a very thin capillary. And in this apparatus, you may reach shear rates of 100,000 and even up to 1 million reciprocal seconds. Usually, you do need this if you do slot coating. If you do roll coating, you need this and maybe a little bit of this. Now, this you already know, but let me show you for completeness. For Newtonian fluids, the graphics are very boring. The shear stress with respect to shear rate is just linear, and the slope is called viscosity. And what we call a rheogram, that is the plot of viscosity against shear rate, is very boring. It's just a horizontal line. So not much actual line. And we will be happy to have that simplicity, but, well, life is complicated. And I mentioned many coatings by design are shear thinning. And also they are, this behavior is also known as pseudoplastic. Now, the curves of shear stress versus shear rate, you see that the shear stress increases monotonically, but the slope, which is the local viscosity, decreases. Now, here is the rheogram, that is viscosity against shear rate. And you always see for shear thinning fluids a region where there is significant change, often over many decades in log-log, where the viscosity significantly decreases with shear rate. Now, it depends on the fluid, but if you just see this behavior, then you can model it with the so-called power law, or Ostwald-Wahl. And it's a very simple model in which you just have two coefficients there, one exponential and one exponent here, that you will use to fit experimental data. Now, sometimes experimental data shows a low shear plateau. Sometimes it presents a high shear plateau, and sometimes you can see both. When you have this kind of behavior with both plateaus, you may use fits of, for example, Carro-Yasuda. It has 5 different parameters that you may use to fit your experimental data. Now, I often receive the question on what viscosity is needed to coat well. But as you may guess now, this is an ill-posed question. And a question that you can only answer with more questions. You may find ranges of viscosities for coating methods cited in literature, but they are anecdotic. They have full meaning only when the geometry is well defined and other liquid properties and operations
Hello. Excuse me, Juan, we cannot hear. Maybe some problem in connections.
So there's some signal problem from the Juan's side, so he would join in the meantime. So just be here. So there are some network issues from couple of week in entire Europe actually. So Europe, Greece. So let's see if he may get connected. Mr. Praveen Das, are you there? In meantime, we can interact to each other. So in the time Dr. Juan rejoined back. Dr. Manoj Kumar Gupta ji.
Yes, sir.
You are from which place?
I am from Mohali, CEC Mohali.
Okay. CEC, this is the CPET, right?
Oh,
No, this is
I think that
The
Chandigarh.
Johannesburg.
This is
Johannesburg, I think.
Mohali. It is
One minute.
in Chandigarh Engineering College, Mohali.
Okay. Yeah.
I think that I lost you for a while, guys. Sorry.
Yeah.
I
No
don't know
problem,
what
no problem.
happened.
We can understand.
Could you hear
We can
the end of the
understand.
presentation?
Yes. We have heard that one. So we were on the slide where we were talking on. Let me see which slide we were there.
Yeah, for some reason it.
Yeah, network connectivity is a big issue. No problem, actually. We can understand that. And
Yeah, did you hear the part on rheology? Because I didn't notice and I continued talking. So,
so that's not a problem.
Mhm.
So I was just thinking that I'm disconnect. Let me. I will tell you where were we.
Mhm.
So rheology part. Yeah, we were talking on the rheology one.
Okay. In which one? Let me show you. Let me present out a window.
So I will tell you the slide number also. Where were we?
Okay. Yeah, I didn't notice that I was disconnected. Sorry. Let me see.
Yeah. It happens actually because we cannot see what's happening at other end. No?
Yeah, since both my screens are used by PowerPoint, then I don't. Can you see
Yes.
my screen?
1 minute. Yeah, we can see. We were here only. So we were on this one, comment on rheology part. So you can go ahead from here.
Okay, so some comments on cotton liquids. Let me go to the beginning. So by design, cotton liquids are shear thinning. And we want the liquids to have a relatively uncomplicated behavior. And shear thinning means that viscosity decreases with shear rate, which is good for the coating process. In fact, if the fact that they have a relatively large viscosity at low shear rates is good to avoid running down as the wet climbs to the dryers and to retain shape under the strong air currents there. But as we know, simple low shear measurements are not enough. In fact, two apparatuses are commonly used in our trade. One is rotational rheometers for ranges of up to 5 or 10,000 reciprocal seconds. It depends on the liquid and the configuration that you use. And capillary rheometers, where the liquid is forced by a piston to move at high shear rates through a fine capillary tube. There, the shear rates can range from 10,000 to 100,000 and even a million reciprocal seconds. The rotational rheometers can be operated under continuous rotation or in an oscillatory rotation with small or large oscillations. And these last may be needed to discern more complicated rheological behaviors such as viscoelasticity. Now, just a reminder, I know that you know this, but Newtonian flows are very simple rheological behavior. The plot of shear versus shear stress versus shear rate is basically linear, and the slope is the viscosity. What we call a rheogram is very boring. Basically, it's just an horizontal line, so nothing to see there. But as I mentioned, many coatings are designed to be shear thinning liquids, the so-called pseudoplastic liquids. In the plot of shear stress versus shear rate, what you notice is that it is a monotonically increasing course, so more shear stress as you increase shear rate, but the slope diminishes. So the rheogram here, viscosity versus shear rate, usually in log-log scale, always exhibits a region in which there is sharp decrease of viscosity over several decades, sometimes of shear rate. When you just see this part of the behavior, your experimental data as power law fluid. But commonly you see some plateau at low shear or at high shear, and sometimes both. For this kind of behavior, usually we model it with the Carro-Yasuda model, which has 5 parameters that you can fit to your experimental data. Now, I often receive the question of what viscosity is needed to coat well. Well, as I showed you, the behavior is not that simple. And as you may guess now, this is an ill-posed question that can only be answered with more questions. You may find ranges of viscosities for coating methods cited in literature, but they are anecdotic. They have full meaning only when the geometry is well defined and other liquid properties and operation settings are defined. In general, coating liquid viscosity varies with shear rate, so a single low shear rate viscosity measurement is often useless and misleading. Now, there is some drive to use more concentrated coated liquids, as then drying requirements are lessened and the process may be faster, but the complex behavior may arise, for example, viscous elasticity in concentrated polymer solutions, and more advanced technique may be needed both for measurements and models. Complex liquids containing particles may be challenging, as particles may migrate under shear or segregate due to improper stabilization. In all of these, particle sizes and shapes matter. Oftentimes, additives used to ameliorate the problems may cause new ones, as they can migrate and interact in unexpected ways. So in regards to designing coating liquids, the only advice that I will give you is keep it simple, or as simple as possible. I want to finish this presentation by mentioning further resources in coating fundamentals, in particular those attracted for both academy and industry. And first, books, of course, books. I think that 3 are basic for our trade, 2 from Drs. Guthoff and Cohen, and the third one by Spicer and Kissler. Then the academic journals and trade publications, from the Journal of Coating Technology and Research to the Annual Review of Fluid Mechanics. If you like the subject, you will enjoy them. And trade publications, here I just mentioned 2, Convertex and ePrint and Converting Quarterly, but many of them available around the world of very high industrial interest. Then there are the courses in academic institutions. Dear to me is the Coating Process Fundamentals short course of the University of Minnesota, an annual event interrupted this year by the pandemic, but one that surely will return to active status. Other important courses and gatherings are those at the Karlsruhe Institute of Technology, also of great quality. There are various symposia, and among the ones that gather industry and academia and are interested in fundamentals is the International Society of Coating Science and Technology. I am the new president of the society for 2 years, although the webpage is not yet updated, as we are planning several changes. We held this year a virtual symposium due to the COVID-19 pandemic. The 21st symposium will be held in Minneapolis, Minnesota in September 2022. You are invited. Then we have the European Coating Symposium. It is also a biannual symposium alternating with the ISCST symposium. Next one is due in September 2021, next year, and will be held in Brussels, Belgium. If not possible to be presential in person, then it will be held virtually. And finally, the Asian Coating Workshop, an annual event driven mainly by academic institutions and industries from South Korea, Japan, and Taiwan. This year, it was canceled due to the pandemic. And with this, I close, and I thank you all for your attention, and I apologize for the many technological issues. So if you have any question, I will be happy to answer if I can.
Very much, Juan. Let the participant ask any question. Do the participant have any question? They can interact to Dr. Juan.
Well, I can
Anyone
say...
wants to have any questions or any discussion with Juan?
Well, I can mention something. If you want the handouts, you can get them from Professor Aria. And and in fact, he can produce also handouts with notes. So so you can review the presentation. And if you have any question, don't hesitate in reaching to me. I will provide Professor Aria with my personal email, and I will be very happy to answer any question or to provide orientation for those interested in going further this line of research.
Yeah, I would like to add one thing, because I am also working in this coating. So actually, as far as the instrumentation machine part is concerned, that how the industry works, and I really learned a lot, because this fluid mechanics, transport phenomena I taught since several years. But how can it be applied for this my own coating field? This I learned from your lecture only today. So how this flow through parallel plate, quet flow, and all these actually would be applicables. Second thing, actually, I'm very grateful to you. The time I sent you invitation, you accepted it, and you also gave a lot of the suggestions, expert name, and I really means. Highly high gratitude to you for that act of kindness, actually.
Don't mention it. No,
And
it's my pleasure. Frankly, I am very happy. Yes, the listeners may not know, but well, I was sick last week, and I delivered my letter late to Professor Aria. But I am just happy to have finished and to interact with you, and it's quite a pleasure.
yeah, you can see that the yesterday night I checked the PowerPoint. It was working fine on mobile, and since today morning when I played on laptop, voice was not coming. So I just installed so many softwares. Somehow it was
yes
not working well.
Yes, even though in my company we use Google Meet, and we frequently do presentations. This is the
Uh,
first time that I try to present with a recording. Now, I was reading in Google that there are ways to do it, but well, we didn't have time to figure it out. But apparently,
yes,
it
yes,
has
yes.
to do with the source of the sound. Somehow, we didn't configure it properly. But well,
And yeah. So the way you have correlated the basic fundamentals of fluid mechanics and transports and to this high industrial level practice, it was really overwhelming thing actually. So I learned a lot from that actually, and these participants also might have learned a lot from here. And at last, you have shared informations just to participate several courses. That is also again very kind actually information so that we can have it, we can participate it. I as CST, I have participated in 2008, and
mhm,
after that actually I could not go actually and participate. So in the last year also I think I got invitation from the Ramdhane, but I could not attend it actually.
mhm.
So we will meet in future personally this ISCST symposium.
Yes, we are trying to look for. Well, this year we were forced to do it virtually. And
Yeah.
we had to cancel almost last minute and then basically learn how to do it virtually. And it was a success. And
Yeah.
we are looking now for ways in which, well, we can have both virtual and presential from now on, but that's still in there. No, a lot of the people is yearning to come back to in-person
Mm,
events
right. Yes. So any
because of the
question from
networking. Yeah.
participant? Yeah. Any question from participant? Because before means Dr. Juan will leave, it is the luckiest time we are having him face to face at least, because otherwise
Mhm.
very hard to get connected. So anyone wants to say something? So if there is no question from any participant side, so I would once again thanks to Juan to be the part of this international short-term course.
Mhm.
We were trying from last 2 months how to manage, and somehow it has worked out. And same thing I would add to Juan that this GD Boras is also facing a lot of connectivity issues. We have practiced with him 4 or 5 times, and then he that decided just to send the recorded videos. So I got from him. So let's see how the things would go for him the live way. But the videos are fine. Those would work well actually.
Yes, as I was telling you, I just read that there is a way to do it. I just couldn't figure it out fast. But there is a way and to present and use the sound from the presentation directly.
Okay. Because I was just connecting this microphone to the speaker only, and from there the sound was coming.
Yes, but
But
it will induce a lot of feedback, and yeah,
yeah.
it will not work that way.
So
Yeah.
with this, I will say thank you once again. We will meet you personally. Thank you. Thank you. Yeah.
Mhm.
So we will meet again at 3 o'clock by for the next talk.
Mhm.
At 3 o'clock we will meet again. Thank you very much. So have a nice day. Okay, sir. Yeah.
Bye.
Yeah.